Hi everyone, this is the presentation of the paper OpenGOP Resolution Switching and HTTP Adaptive Streaming with VVC at the PCS 2021. I'm Robert Skupin from Fraunhofer HHI in Berlin, Germany. HTTP Adaptive Streaming is one of the most important paths of video distribution nowadays. For it, content usually is temporally segmented, and each segment is encoded at various bit rates or resolutions to fit the needs of the various clients. A single client can then switch between variants of each segment it downloads over time, depending on, for example, the observed throughput. With H.264 and H.265, changing the resolution within a coded video would require a break of the temporal prediction chain. So in order to enable seamless switching of a client, an encoder would have to place frequent random access points within the video, and segmentation would occur depending on the position of those. This would allow the seamless switching functionality, but of course it comes at a severe coding efficiency impact. Now H.266 or VVC was finished last year, and it has this new feature referred to as reference picture resampling that will allow changing the picture resolution without a complete prediction break. So this feature should enable us to be much more efficient in HTTP streaming, and this talk will show you how it's done in detail. To better understand the potential issues, let's first have a look at VVC prediction structures. Here on the left-hand side, you see a figure that illustrates the pictures of two consecutive segments and their prediction dependencies. It's also color-coded, so you can notice that each segment has an orange block, one of these random access point pictures we mentioned earlier. Let's focus on segment 0 first. You can see that each of the trailing pictures, the blue blocks in this figure, they depend only on the random access point picture of this segment or on other trailing pictures. So this is what is called a closed-GOP coding structures with no prediction dependency to earlier GOP structures or segments. In segment number 1, you can see that the leading pictures, the yellow blocks, have prediction dependencies on the wrap picture of this segment, but also on the last trailing picture of the earlier segment. And this is what makes this prediction structure much more efficient. In terms of numbers, you can see on the left-hand side some results here that we gathered from the open source VVC encoder VVenc. And for setups that are similar to what is done in live streaming with very short random access point periods of, for example, 1 second, you end up with 9.2% BD rate gain over using closed GOP structures. And even for longer wrap periods, as they are common in video on demand services, here in this example, it's 4 seconds, you end up with 2.35% BD rate gain over closed GOP structures. So what happens when we use these efficient OpenGOP coding structures and perform bitstream switching with them? Here on the right-hand side, you have a figure that illustrates bitstream switching based on the QP, or the bitrate. It's noticeable that the leading pictures, the RASL pictures here in the middle, they are reconstructed with severe drift artifacts. It's especially noticeable in the difference pictures, but also on the bottom in the PSNR domain, you see a clear drop here. So there are artifacts. And these stem from using different reference pictures now on decoder side after switching than what was used on encoder side during encoding. These reference pictures, they do not only differ in terms of the actual reconstructed sample values, but they also have completely different syntax, different motion vectors, different partitioning, and so on. So using them as prediction source will ultimately lead to prediction drift, of course. Now in VVC, you have a whole zoo of different coding tools, and each of them uses the reference pictures in a different way. You have the more traditional type of prediction from sample to sample, block-based, motion compensated, copying of sample values from the reference pictures. And these tend to not create very noticeable drift, but there are also more fancy tools that create or predict syntax from syntax or even syntax from sample values. And these tend to create very noticeable and disturbing artifacts. And of course, any coded video data stream, it has a lot of control data, and this also has to adhere to whatever conformance constraints are formulated in the specification, or otherwise you may end up with not only drift but decoder crashes. With that in mind, let's take a look at reference picture resampling, or RPR, the new feature of VVC that will enable OpenGOP resolution switching. There is a set of constraints defined in the VVC standard that relates to different coding tools and that needs to be adhered to if RPR is supposed to be used in a picture. For example, the optical flow related coding tools, BDOF and PROF, they need to be disabled with RPR. Decoder side motion vector refinement, which refines motion vector in the current pictures depending on the sample values of the reference pictures. This needs to be disabled too. And for temporal motion vector prediction, TMVP, or the new sub-block TMVP in VVC, there needs to be special care when selecting the reference pictures so that they do not potentially change their resolution. All these constraints are well defined in the VVC standard and it's clear how to apply them. For example, in a continuous encode, how you see it in conversational scenarios. When you want to switch resolution without breaking the temporal prediction chain, it's very clear how to use the RPR feature in VVC. However, for streaming scenario, there has to be a little more thinking. Basically, on encoder side, each picture that may potentially see a reference picture with a different resolution needs to adhere to these constraints up front so that when on client side, the decoder sees a concatenated bit stream where the QP switch occurs or a resolution switch occurs, then it does not lead to a non-conforming situation. So let's imagine we did just that and adhere to the RPR related constraints for all the leading pictures in our setup. And now we put everything on the server and the client starts to download. And in this example here, the client switches between two QP points, two bit rates constantly. In this figure, you see the 600 pictures over time in this video coded sequence and PSNR on the vertical axis. And the three colors are the YUV components. You can clearly see the Luma PSNR switching between the two QP variants. But also you notice in the RASL pictures that there are, in the leading pictures, that there are certain artifacts and clearly a severe PSNR drop is noticeable. Let's have a look at what this really looks like. Here an example from a coded video sequence with a lot of motion. And you can clearly see there are artifacts in the color component channels. And the culprit here is the cross-component linear model, or CCLM. This tool in VVC allows to predict the chroma component signal from the Luma component signal. It's only used for intracoded blocks and relies on the neighboring samples. In a sort of samples to syntax prediction, it derives model parameters from sample values. The three-step process goes like this. First, the Luma block and its neighboring reconstructed samples are downsampled. Then the derivation of the model parameter is based on these neighboring sample values. And the third step is then to apply this model to get a chroma prediction signal. Let's look at the parameter derivation for CCLM a bit more closely. Here you see the linear model with parameters A and B, and they in turn depend on xi and xs, which are the average of the two largest and two smallest neighboring Luma sample values, and yi and ys, which denote the average of the corresponding chroma sample pairs. This is really the issue here, that this process relies on extrema of the neighboring sample values. So when the reference picture has a small deviation, the parameters of the model have different values, and in turn this can lead to a huge amplification and visible artifacts of the deviation in the Luma samples to result in these extreme chroma artifacts that we noticed in the video. The issue is here that CCLM can only be switched off on a relatively high sequence level, and this comes at substantial coding efficiency losses of 3.4% BD rate. This is due to the intra-coded pictures using CCLM for roughly half of their CUs. And this leads to the constrained RASL picture encoding method that is presented in this paper. It combines the RPR-related coding constraints for tools like BDOF, PROF, DMVR, and TMVP, together with a constraint on CCLM, which is disallowed for any CU in a picture that is supposed to use RPR potentially on the client side. And with this constraint encoding method, we are able to achieve still the major fraction of the OpenGOP related coding gains. Roughly for the short RUP period, it's 8.57% BD rate gain compared to 9.22 for regular OpenGOP coding with the artifacts we noticed. And for longer RUP periods, like in VOD, still roughly 2% BD rate gain, where unconstrained encoding results in 2.35%. So going back to the example from earlier, where a client constantly switches between two QPs, here you can see the results when the constraint encoding method that's presented is applied, and there are no more artifacts in the chroma components that the client decodes. Another interesting observation is the objective quality at these switching points. The quality switches gradually from one representation to another, instead of this abrupt switching that we are used to from HTTP streaming. And here this figure shows averaged over all sequences, switching points, QPs, and resolutions, the average ups and down switching behavior compared to the PSNR of the OpenGOP and closed-GOP variants. And it's visible that for up switching, there's a really gradual transition from one quality to the second quality. And for down switching, there's a rather sharp drop with the first leading picture. And this may be due to the downsampling, the involved downsampling of the reference pictures, which introduces a sudden quality degradation on its own with the first picture. So in summary, VVC will allow OpenGOP resolution switching and HTTP adaptive streaming. And this paper presents the constraint encoding method of leading pictures with related constraints to BDOF, PROF, DMVR, CCLM, and TMVP. It comes with substantial coding efficiency gains compared to closed-GOP coding. And this method has been integrated into the open source encoder VVEnc already. Thank you very much for your attention, and please get in contact if you have further questions.